Hi all, we will wait till 6:05 and after that I will start this lecture. Hello, am I audible? Hello. Can someone confirm if I'm audible or not? You can write in the chat also. Okay, thank you. Give me 1 minute. Other things. So can do 1 minute. Just give me 4 minutes. So is my screen visible to all of you? Can somebody write in the chat? Hello. Please write in the chat if my screen is visible or not. I request you to write in the chat so that we can start the session because I will not be able to know if my screen is visible. Okay. Thank you, Sunny. So hello all. My name is Manoj Shikhar. I am a PMRF scholar at IIT Delhi. I'm in the Applied Mechanics department and I have done my BTech and MTech from IIT Kharagpur. I will be taking your live sessions on solid mechanics on every Tuesday. And first, I will recapitulate whatever has been covered in the videos in week 2. And after that, we will solve some problems. So many people were asking in the forum that from where they can get the notes, whichever sir is covering. So you can follow this link. Here you can find the notes of all the lectures sir will be covering in future also. And one more thing, last time somebody asked me that will there be some questions related to gate or not? So in these PDFs, there are some questions at the end, maybe in the last of the PDFs. So there are a few questions which you can solve, and they are like designed so that they can be asked in the competitive exams. Apart from that, I'd like to declare one more thing, that you people are given some assignment every week. And though this is a doubt solving session, please do not ask those questions from us, like from me or from Roshan, the other TA. We have strict instructions that we cannot help you with those assignments because those are graded assignments. So now I will move on to the next slide. So in week one, we came to know that the stress tensor, it can be represented in the matrix form. And though the stress tensor is like not changing, but the matrix form changes according to the coordinate system. So the general question arises that how do we relate stress matrix representation of stress tensor in two different coordinate system? So this is what has been covered in the first lecture of this week, and there will be few slides related to that. If you people have any doubt, you can directly ask me, maybe in the chat or maybe by unmuting yourself, and I will try to help you. And suppose if I'm not able to help you right now, then you can also write in the forum, and there also I will reply any question related to my session. So let's start. So we know that the stress matrix representation can be written like this. So this is the matrix representation written in E1, E2, E3 coordinate system. So always remember, we have to write the coordinate system at the bottom of the representation. This helps us to identify that in which coordinate system actually this stress matrix is written. You can see that in other coordinate system, E1 hat, E2 hat, E3 hat, we have a different notation. So as you may remember from last week's lecture, the first column is represented by the traction on a plane whose normal is in even direction. Similarly, the second column of this stress matrix is constituted by the traction on the plane which has E2 as its normal. And so the same goes for T3. For this case, this is the traction on plane which has normal in E3 direction. Now, if we consider E1 hat, E2 hat, E3 hat coordinate system, there these components of T1, T2, and T3, they will be different. Why? Why should they be different? Because like if you think mathematically, you can understand that the first column in E1 hat, E2 hat, E3 hat coordinate system will be written according to the new coordinate system, that is EI hat. That is for example, the first column will be written with respect to E1 hat. It will be written on a plane which has normal in the direction of E1 hat. Now, if E1 and E1 hat both are different, then of course this will be different. The same goes for T2 hat and T3 hat. Later on in this slides, we will also see that how will you verify that the stress tensor which you have calculated is correct or not. Like the new stress tensor, the new matrix representation of a stress tensor you have calculated is correct or not. So going to the first week only, we can represent a traction on a plane with normal n by this equation. So how can you write tj hat dot ei in terms of tk? So one thing to note here is tj hat, when we are replacing this. So here this equation is for any general n, right? So I can replace n by j hat, that is n equal to ej hat. So this thing should be clear that how this equation has come. So what we are trying to do, we are considering that E1, E2, E3, initially whatever we have, we know the tractions on that coordinate system. So what do we know? T1, E1, T2, E2. sorry, the traction on T1, like T1, this is the vector only. Then T2 on like E2 plane and T3 on E3 plane. So one thing I'd like to clear here is whenever I say T1 plane or E1 plane or E2 plane, it means that E1 is the normal of that plane. If I say E2 plane, it means that E2 is the normal of that plane, and so on. So what we did, we wrote this Tj hat in terms of traction which is present in E1, E2, E3 coordinate system. Now this is a dot product. So this part is a scalar. Ej hat dot ek is a scalar. And similarly, the whole thing will be dotted with ei hat. So what we can do, we can dot this tk with ei hat. Why? Because this thing is a scalar. A scalar can move here, here, anywhere it can move. So overall, we are getting a scalar here. And that is correct also because we are writing one of the components of matrix, sigma ij hat. Other relation you should keep in mind is the how the transformation has been done. So ei hat is written as a rotation tensor multiplied with ei. Till now, anybody has any question or any doubt? And other equation with other like equation you should know is like how do we extract an element of a matrix or an element of a second order tensor. So to extract CMN, first we will have to multiply that tensor with En vector, and then we have to do dot product with Em. So these two are one of the most important relations, and down the line when you will study this course, these things will be used extensively. So in matrix form, ei hat can be written as ei hat in E1, E2, E3 coordinate system, R in E1, E2, E3 coordinate system, ei in E1, E2, E3 coordinate system. So what does this mean? Ei hat in E1, E2, E3. Like the components of this vector will be with respect to E1, E2, E3 coordinate system. For example, let me open a OneNote so that I will be able to write also. So suppose this is E1, this is E2, and this is E3. This is E2 hat, sorry, E1 hat. This is E2 hat. And for now, let us assume for simplicity that E3 and E3 hat they are coinciding just for this, like this case. Now, what you can say, suppose if I wanted to write E1 hat in coordinate system, what will be its matrix form? Can anyone say? Like you have done week 1, and I think you should be able to answer this. So it should be what? 1, 0, 0. Right? But if I write E1 hat in E1, E2, E3 coordinate system, it will be something else. It will be something here, something here, something here. But it will not be 1, 0, 0 always. Maybe a special case can come when this theta is 0. At that time, we will get E1 hat in both the coordinate system as 1, 0, 0. But here we will have some value. Let us assume x1, x2, x3, something will be there. So So here we have to write with even hat or EI hat in E1, E2, E3 coordinate system. This rotation tensor is also written in E1, E2, E3 coordinate system, and this EI, it is in E1, E2, E3 coordinate system. As an example, here it has been shown that how will you find E1 hat? So this exercise is actually done so that uh, we can find a relationship between these, like the elements of this rotation tensor. You will see later on that why do we do that. So E1 hat equal to R into, since here it is 1, so it should be even. So 1, 0, 0. So we get a column R11. Basically, we get the first column. So R11 is what? E1 hat dot E1. R21 is E1 hat dot E2. And R31 is E1 hat dot E3. So we can write Rij as Ej hat dot Ei. Now this relation, we will put it here. So if I have to write Ej hat dot Ek, what should it be? We will replace this index I by K. So this will be replaced by Rkj. Now this Tk is a vector. So we can write it in its own component form. So how did we do that? We wrote Tmk Em dot Ei hat. Now again, you will see that there is Em dot Ei hat. So what you will get? Tmk Em dot Ei hat. This is same as dot product. Can we write it as Ei hat dot Em, because A dot B is B dot A. So what will this be? This will be RMI. You can see here Rij was Ej hat dot Ei. So RMI should be Ei hat dot Em. You should be well versed with this index notation. If you like practice, it will be very, very easier for you in the future to understand the concepts. So you can see here what we have: RMI, TMK, RKJ. We know that TMK, what is TMK? If you remember the stress tensor or the matrix representation of a stress tensor, the first column was what? This was made using T1. This was made using T2. And this was made using T3. Right? So T1M, suppose if I replace K by 1, so T1M can be what? It can be either T11 or T12 or T13. So what will it be? TMK should be sigma, like this was the matrix representation of sigma. Okay, so TMK should be what? What are these things? These could be one of these entries, right? One of these entries, something, one of these entries. So this will be what? T31 will be here. This is T31. This means what? This is, and if we write in the matrix form, like what should it be? Sigma 1 1, first row, then sigma 3 1, and so on. So TMK will be what? Sigma MK. So we get this formula, and this is one of the most important formula for a stress transformation. Here the stress matrix representation of stress tensor in E1 hat, E2 hat, E3 coordinate system, E3 hat coordinate system is related using this formula. And one thing to note is these R is in E1, E2, E3 coordinate system. Always remember this R has been written in E1, E2, E3 coordinate system. Hello. Sorry, there was some internet issue from my side. Uh, Sorry for that. So this R is in E1, E2, E3 coordinate system. This sigma is in E1, E2, E3 coordinate system, and this sigma is in E1 hat, E2 hat, E3 hat coordinate system. Now, if you go in the textbooks, you will find that there are some formulas given in terms of cos theta, sin theta, and at undergraduate level, most of the colleges they teach like that. They teach you using some formula of cos to sin to theta and all. But this is the most generic form, and if you know how to use it, it's really simple to solve any stress transformation problem. So, so that's why I prefer this particular formula only. Earlier, we used to use that, like the formula in terms of theta and all. Now, one important thing to note is that E1 hat, EI hat, it transforms as R into EI. But any other vector V, it will transform as R transpose V1, V2, V3. This can be proved also. So I'll just show you a quick proof that how do you do this. So we can write V as summation of Vk, Ek. We can also write it as Vk hat, Ek hat. Now we know one thing that vector is a tensor and this will not change. Other thing what we know is Ek hat equal to R Ei. Sorry, R Ek. So what can we do? We can replace Ek hat here. So we can write V as now we can pre-multiply R transpose. Or one more thing you may remember is it is a property of rotation tensor. I hope you all remember this. And this comes a lot. This becomes handy at lots of situations. So what we can think is like there is one identity tensor here. What is this? This will give me the same vector. If you operate a vector on an identity tensor, you will get the same vector. Okay. So what we can do, we can write it as Vk R transpose R Ek equal to so from here we can say that V hat is R transpose time. Anyways, let's move on. So this was the examples I discussed in the class, and I thought that this is a good example, so I also kept it in my PPT. So this sigma was given in E1, E2, E3 coordinate system, and it was told that the old coordinate system is the, like, we get a new coordinate system by rotating our old coordinate system by 45 degree. So this is the rotation tensor, matrix representation of rotation tensor. Uh, you can get this formula like cos theta minus sine theta, cos theta. And because it is rotated about E3, here you can write 1, 0, 0. Now, if it was rotated about E2, the representation will be different. You can search on the net also, or you can try to use the formula Saras taught in week 1. And from there, we get that the new transformed stress is root 2, 0, 0, 0, 0, 0, and 0, 1, 1. What does this shows us? This shows us that in the new coordinate system, T2 hat, it is 0. Like there is no traction on the new, on the plane which has normal as E2 hat. Now you can also verify this. How do you do that? You know that, like earlier we have shown the formula of Tn, like on any plane, what will be the traction with respect to 3 tractions on 3 planes. So T2 hat can be found out using this formula. You can also, you also remember from the like dot product of lecture that A dot B can be written as AB cos theta. And if you put like all the angles correctly and all, you will find out that T2 hat is 0. So this was the recapitulation of lecture 4, like the first lecture of week 2. Now, after that, we studied about linear momentum balance. In linear momentum balance, the basic key concept was the Newton's second law of motion. And one more thing that was considered while solving this, the linear momentum balance, was that we considered while deriving this linear momentum balance was that we considered a small cube or cuboid, and we found, like, we analyzed that how this will be deforming, like at different points, what are the stresses and all. So when you solve, so keep this in mind, when you solve the linear momentum balance equation, you will get stresses at all the points. You can get stresses at all the points on the body. It is so here it is represented here like in some. So this X, we are considering that the cuboid's centroid is located at X. Now, what kind of forces will act on this cuboid? The forces which can act on this is the contact force, that is contributed by traction, and non-contact force, that is the body force, and the acceleration part, the dynamics part. So what we do first, we try to find out that what will be the contribution of traction part in this total summation of force external. So traction acts only on the boundary. Remember this, traction will act only on the boundary of the body. It will not act in the volume. So we have to find the force due to traction. We will have to integrate it on the boundary. So in this case, it is the surface area. Suppose if it was a 2D body, so in that case, it would have been a line element on which you have to integrate the traction. So for a generic case, the 3D element, let us assume we are trying to find the contribution of traction on even plane. So what will happen if you go for even plane? In this plane, you're fixing the value of X. This X plus delta X1 by 2, it is fixed. Now, if you move in at any other place, this point will have a coordinate X plus delta X1 by 2, comma, the coordinates of y and z will change. So xi and eta. So that is what is written here. So this part, the part which is written here inside, this is the like representation of this point y. So T1, the traction on this face can be written in terms of stress. So remember, stress is a point function. It does not depend on normal. So here you can see that we have directly written it as a point. Like we have directly put in the point here. And what is the normal of this plane? No, the normal is even. So T1 can be written as sigma even. Other thing you should know that we will how to do Taylor's expansion. So here Taylor's expansion is used and sigma x plus del sigma x1 by del sigma by del x1 into delta x1 by 2. So this is this part is like expansion with respect to x term. Now for y term, this will be del sigma del x2 into xi. For z term, it will be del x by del x3 into eta, and there will be higher order term. As you remember from Taylor series, we sometimes like neglect those terms, and we generally find error. Like in maths 1, we used to also find the what is the error of in the value if we are neglecting that those terms. So the total force, as I told you, will be traction, this traction into area. Now, what will be the area of this? Suppose if there is a small rectangle here, the area will be d xi into d eta. Why? Because the x is fixed. We are not varying x. So the area is d xi into d eta. We will integrate it. The limits will be, we are considering x, the centroid of the like cuboid at the center. So to find the x2 limit, we will have to go up by delta x2 by 2. We have to go down by minus delta x2 by 2. To find the limit for delta x3, we will go minus delta x3 by 2 and delta x3 by 2. So that is what has been written here. Now, if you look at it carefully, you will realize that this part does not depend upon x2 and x3. So we can directly take it out of this integral and we can integrate it. So this part into E1, we took it out and we integrated this. What will be this? The area of the, this is the area of the face. Similarly, if you look at it, and you may have read this in definite integral, that del x by del sigma by del x2, this will be independent of your x2, but this xi will be inside. Now only xi, like if you remember this formula of definite integral, it should be 0. Why? Because this function is odd function. And odd function, when it is integrated from minus a to a, it becomes 0. Even you can prove it here. This is a very easy function. So the integration will be this. So that is the reason this term and this term will vanish. And at the end, we will be getting sigma x E1 del x2 del x3 plus this part. Similarly, we found the we found the total force contribution of traction on negative E1 plane. And we found out that this is minus sigma E1 delta x2 delta x3 and this term. So if you add both the forces, so you will get the net force contribution due to traction from E1 plane and minus E1 plane. So this is what we get. And if you solve for other directions also, like if you solve for other planes like E2 planes or E3 planes, you will get this final equation. So see here, when we were working on x1 plane, we had del sigma by del x1. Now we are working on x2 plane, so we will have del x2 by E2, and the normal is E1. So this is the key, that how to find that on which plane the force is acting. Now the body force is a force which acts on the volume. So here body force has been integrated over the volume. And the same concept, we do the Taylor's expansion of body force. We see that this part is independent of gamma, xi or eta. So this comes out and other parts are here. And the same concept that since these are odd function, so this will go away and this will become 0. So we finally have B delta V plus small o delta V. Small o delta V means when limit delta V will tend to 0, small o delta V by delta V will be 0. Means the small o delta V terms are very small compared to delta V. Similarly, for the dynamics part, we first write the equation of linear momentum. So the total linear momentum will be what? Mass into velocity. So mass can be written as rho dv, and then we can replace this volume by this d xi, d gamma, d xi, and d eta. So if you follow the similar procedure, what you will have to do, you will have to differentiate this linear momentum. If you differentiate the linear momentum, you will get the force, mass into acceleration. That the RHS part of the, generally we say mass into acceleration very casually because we have been taught like that. But ideally the right hand side part should be dp by dt, the rate change of momentum with respect to time. So in solid mechanics, generally the mass is constant. So we can directly say mass into acceleration. So if you follow the similar procedure, you take this time derivative inside the mass. So here look at one thing. When we are taking this time derivative inside, we are working in the mass domain. Why are we working in the mass domain? Because mass is not changing. If I write it as rho into volume, rho into small volume, the volume is changing, but the mass is not changing. So that's why we are, while taking this time domain inside, we are keeping our integrals in mass domain. And later on, after doing all the things, we replace this mass domain using volume domain. And finally, if you follow the similar procedure, you will get that you are getting rho ax del v plus small o del v. Now we are adding all the components of external force, like the from traction from body, that will be equal to the rate change of momentum. We divide both the sides by delta v, and what we get this equation. Sorry, here we have just combined this small o term, but later on if we divide by delta v, we will get this equation, and this will be 0 in limiting condition when limit delta v tends to 0. So the final linear momentum balance equation is this. In scalar form, scalar representation, like each equation can be written like this, and you can see this was the contribution from the first part, like this was the contribution from the total force on E1 plane due to traction, E2 plane due to traction, and E3 plane due to traction. This was the body force in direction B1, B2, B3, and A1, A2, A3 are the acceleration of center of mass in, remember, this is the acceleration of center of mass in direction A1, A2, A3. In some books, you may find that instead of B1, it is written rho B1. Here it is written rho B2. Here it is written rho B3. So there, B1 is force per unit density also. So rho A1, when we write rho A1, we multiply it with dV. So A1 is multiplied with mass. Similarly, when in some books they write rho B1, you can consider there that B1 is also like acceleration. It is not the acceleration, It is like some acceleration term. So force by mass kind of thing will be there. So for units, they will be different. And you can see one more thing. For example, if suppose there is gravity acting, so because we are writing body force, so the first thing which comes into mind is the gravity. So suppose if gravity is acting in third direction and other directions, it is zero. So this will be 0, 0, g. Now, depending upon the direction, like if it is acting in minus E3 direction or plus E3 direction, it will be minus g or g, depending upon the direction. Now, the same procedure will be followed for the derivation of angular momentum balance. In angular momentum balance, we do the net change, the total external torque will be equal to rate change of angular momentum. So this was called linear momentum balance because we were using Newton's second law, and there we see the rate change of linear momentum of the body. Here we will, this is called angular momentum balance because here we are seeing the rate change of angular momentum balance, angular momentum of the body. Excuse me. So to write the angular momentum of a point, what do we do? Angular momentum of a point is R. Like suppose if I want to write the angular momentum of, I will write it here possibly. Suppose there is a particle, it is moving with velocity v like this, and observer is here. This was some 11th, 12th questions. The mass of this particle is m. So the angular momentum of the particle will be given by what? R. Suppose this point is A, this is B. BA cross the linear momentum. So RBA will be what? Suppose if there is some origin here. So RBA can be RB with respect to origin minus RB with respect to, sorry, RA with respect to origin cross with so L equal to, so in this case, in our case, this Y is basically the position vector of our final point. So we will replace by Y minus X cross MB. If anyone has any doubt, they can like write in the chat, they can ask me directly. So the same thing will be replaced here. It will be replaced here. Now that this thing was done for a body moving with a small point moving with a velocity v. Now for force, how do we do it? So what I showed was the right part, like that will go in the right part. For force, we know that if suppose there is a force acting, suppose there is a force acting and the observer is here, right, somewhere here. The force is acting at point P and it is at Q. So what will be the torque? Torque or moment, whatever you say, it will be R PQ cross F. So this will be the force. So what are the forces that are acting on the body? We discussed it is traction force. Force due to traction. Contribution from traction. Force contribution from body force. Or third one will be the dynamics part, which will be on the right hand side. So the body is accelerating. So those three cases will be dealt here. So the force due to traction will be what? Traction into the area on which traction is acting, cross with y minus x. Same thing, y is what? For traction we saw, we are working on a plane. So in this case, y will be x plus delta x1 by 2 xi eta. So that is replaced here. Then it is getting crossed with the traction part. And we saw how we can write traction in terms of a stress matrix. We wrote it there. You take the cross product, you will see that this part and this part will be independent of xi eta and it will be coming out. Then there will be some other part. So if you work it out, you will get torque because of traction on plane 1 will be even cross sigma even delta v by 2 plus small terms of volume delta v. Similarly, t minus 1 x will be the same term. So if you add them, you will get even cross sigma even delta v or delta v. Now, one thing which I have seen many students doing, so this is the mathematical part. So I will like to mention here. I just remembered it. So suppose there is some matrix J. Let us assume there is some matrix J. If you're multiplying this by some vector A, you will get a new vector. Suppose we are getting a B vector. So B vector is not equal to A. In some special case, when J is identity, it will be equal. But in general, it is not equal to A. But what I have seen kids doing is they will do what? Suppose there is a cross product, for example, in this case. So if there is a cross product, A cross A, this is 0. We know that A cross A is 0. What they will do? They will do this one also. A cross J A. They will write it as 0. They will just take this A inside and they will write it at 0. But this is wrong. Wrong. We cannot do this. This is a new vector now. This is not this old same A vector. And the best example of this is the transformation we do for Cartesian coordinate system. Here, this is a tensor, second order tensor matrix represented in the matrix form. This is the one of the vectors, a special vector, of course, in the direction of E1. These two are not same. You can see it from here. So always keep in mind whenever you are solving the problem, and most of the people do this when they find a cross product, they will directly write it as 0, but this is not right. Keep this in mind. Similarly, if you analyze for the body force, what will happen? Body force will act on each point of the body. It acts everywhere. It does not act only on the boundary. So body force will be, suppose in case of traction, this was where y was being considered. This was where y was being considered. In case of body force, the whole volume, anywhere it can appear. So suppose if I'm considering this as y and this as x. So here y will be what? Y will be this will be y. So y minus x can be replaced by xi e2 plus eta e3. Here it will be gamma e. So that net क्यों चला गया? Sorry if my net had gone in between. I don't know why is it happening today at my institute. So are you able to hear me now, or is my screen visible? Can somebody comment on it? Okay. I hope you people are able to understand whatever I'm telling. If you have any doubt, you can write in the comment in the chat box. You can ask me. Uh, After this revision, I will give you a short break of 5 to 7 minutes, and then I will solve some problems to give you a feel of like how to deal with how to use these theories. So I just recapitulate so that every time, if you don't remember what are the concepts, it will just refresh your memory. So, so if you solve all those things, you will find out that the body force will be of small o delta v. That is, it will be very small compared to delta v. This is the same. So for a point, I showed you that this will be the linear moment, sorry, angular momentum equation. R, it should be yx actually. Sir had written r/o in the lecture. That's why I wrote it like this. Now, the total angular momentum will be this, the total angular momentum, because we are considering a 3D body here. This is for a particle, so we will have to integrate it over the whole volume. Now, again, the same concept. While differentiating with respect to time, keep this in mind. If you keep this in mind, and if this derivation comes in the exam, it will be very fruitful for you to remember this line, which I'm telling. Whenever you are differentiating with respect to time, always keep the integral such that this part, like for example, here it is mass, here mass is constant. That's why we are able to take, and we are integrating over the mass domain. That's why we are able to take this dt inside this. Suppose if this was the volume domain, then this volume itself is changing with time. In continuum mechanics, like in higher education, this is called Eulerian formulation. Generally in solid mechanics, we read Lagrangian formulation. So I'm just giving you some few words. Don't bother about that. I'm just telling you. So the mass is constant. That's why we are keeping our integrals in terms of mass whenever we are taking this dt inside. When you took dt inside, first you have differentiated this. Then you differentiated this velocity part. And that's why here it is ay. Now what is this vy? Vy cross vy, it will be 0. A cross A is 0. That's why this term vanishes. Now, after we know that, okay, this is the term we have, we can convert our integral to volume domain. And that is what has been written here. And you can see that this has the exact same format what we had in our body force integral part. Where is it? Yeah, here. It's this similar format. So when you solve later on, you will get that this is also a small o delta v. So now we are rearranging all the terms together. We are clubbing all the terms together, and we are dividing by delta v, and we are taking a limit delta v tends to 0. Do you know why do we take limit delta v tends to 0? Because these expressions, they are true for any volume. Like they're true for a delta V of 1000 m³ and they are also true for like almost zero volume. That's why we are taking this limiting condition. So for any volume it is true. That's why we are taking the limiting condition, and from there we get angular momentum balance equation. And you can see that even if acceleration A was present, even if the body force B was present, I should say body force with per unit volume. So then also we are getting this equation. So this equation holds even if body force is acting or even if the body is accelerating. Now, what is the consequence of angular momentum balance? The consequence is that we come to know that the off diagonal terms of this stress matrix, they are equal. So if it in general, a 3x3 matrix has total 9 components. So what do we come to know? This will be tau 21, this will be tau 21. This will be tau 31, this will be tau 31. This will be tau 32, this will be tau 32. See, these are equal. This means that stress matrix is symmetric. Sigma is symmetric. Now, this is what we teach in UG courses, because here we do not go for higher deformations. But for larger deformation, this will not be true. But for you people, you remember that sigma is symmetric as a consequence of angular momentum balance, because of angular momentum balance. And this helps a lot in solving many problems. Sometimes even sir has discussed one of the problems in the video lectures. If you have gone through it, you may have seen this problem that suppose if this is some body fixed here and sir is and we are applying some traction T here. So near this point near this surface where we are suppose if you are considering a point very near to this surface. Suppose we are applying traction here, T0, and we're considering point very near to the surface. If you solve this problem, you can go and watch in lecture 6, I will tell you. You will find out that in third direction, the traction is T0. So one thing you should like remember while watching that video, this T0, this was applied externally. Applied externally. And these things, whatever you will find like T1, T2, T3, which you will find. These are the internal response of the body. Internal response. These are not something we are applying from outside. What we applied was this traction T0. And interestingly, in this case, you will find that this will be equal to T0. But you like many times people will say that, yeah, this is like action reaction thing. We can see that T0 is acting outside. But this is something external. This was not the response of the body. So we cannot directly say that this will be equal to this. We need to use the equations we just saw to actually claim that these two will be equal. I request you to go through that problem. That is a very interesting problem and it will clear your concepts. And one more problem which sir discussed was the of hydrostatic pressure. So suppose in fluid pressure is acting. So fluid cannot sustain. Fluid can't sustain shear. What does this mean? All of diagonal terms 0. of diagonal terms 0. If you keep these concepts in mind, sometimes they have asked, I think, a similar type of question in GATE a long time ago. So if you are solving some problem for GATE, you may encounter this thing. They will give you a fluid. That means that it can a static fluid, of course, not a flowing fluid. You should remember that when I'm here, it is a static fluid, not the flowing fluid. So off diagonal terms are 0. And what will be the terms in this diagonal? So it will be minus Pi, minus P. This sir has derived mathematically also there in the video. So I urge you to go and look at that video. Now we will take a small break of 5 to 7 minutes and I will again continue and I will show you some of the problems from the link which I have given in the second slide. Here at the end you can find some problems also at the end of the PDFs. So I will deal with 2-3 problems from that PDF or maybe more, and then you can practice from there. So let's take a break of 5 to 7 minutes. Thank you. So hello all. So let's restart our session. So let's first deal with the subjective questions. These questions are meant to be practiced by you, so I will be dealing with few of them and others you can try. So for example, I will be doing question number 2 for you, just to give you a gist. So what is, yes. Am I audible to all of you? If anyone can just say yes or no. Or you can write in the chat because I had muted myself. I hope I'm audible to all of you. Anyways, so the question states that suppose the traction on a plane with normal A is given by TA, while on a plane with normal B is given by TB. Furthermore, the two plane normals need not be perpendicular to each other. Prove that TA dot B equal to TB dot A. So question number 2, lecture 6 NPTEL. Question number. So they have given what? They have given you a traction on plane with normal A. TB traction on plane with normal B. Okay. So they are telling you to prove now. A few concepts will be used here. First of all, can we write traction as this? Now they're telling that from a point, let us assume we have a point and here, sorry. And from this point, there are different planes passing. So for this plane, the normal is this. Suppose this is B. And for this plane, the normal will be this. They are not perpendicular. A is not necessarily perpendicular to B. So they are also telling that A is not perpendicular to B. A is not necessarily perpendicular to. So we know that we can write traction like this. So TA will be what? Sigma x into A. TB will be what? Sigma x into. So first we use the concept we studied in first week. This is the concept from first week. First week. Now we have to do TA dot B. So what will be this? Sigma x into A dot B. Again, do not dot these vectors directly. This is a new vector. This is a new vector. This is not just A. So this is a new vector. I write it like this. This is a new vector. Now we can write it like A dot sigma transpose B. Now, can you people prove this, that sigma A dot B will be equal to A dot sigma transpose B. From matrix method, it is very matrix method. You will write what? Sigma into A transpose B. Sorry. So this is what? This is a something new vector, right? So we can write it as sigma. I am dropping this X to shorten my notation. A transpose into B. So what we can do? We can write it as A transpose sigma transpose into B. So this is what? A dot sigma transpose into B, a new. So TA dot B is A dot sigma transpose B. Now from AMB, what do we know? This is the concept read in lecture 6. We know that sigma is symmetric. This means sigma equal to sigma transpose. So what will be this? TA dot B will be A dot sigma. We have to find TB also. TB dot A. So TB dot A is what? TB dot A is sigma B dot A. Now this is same as A dot TB. Same thing. So we can write it as A dot sigma B. So you can see that TA dot B equal to A dot sigma B and TB dot A equal to A dot sigma B. So these two are equal. So we have proved it. Now I have used matrix method here, but of course you can use indicial notation and you will get the same result. Like you should ideally get the same result, and I leave that to you, that you prove that this equation is true. I will tell you what to prove. You have to prove that B dot AB, sorry, B dot AU equal to A transpose dot A transpose V dot U. Prove this as homework using indicial notation. Prove this. So we are done with the first question. Now let's see if any other question I want to do. So let's solve this question number 10. So it says that in the absence of body forces, does the following stress distribution satisfy the equations of equilibrium? So in this case, you have to check whether this stress matrix representation, this satisfies our linear momentum balance and angular momentum balance. So the best thing to do is first you see if it is satisfying angular momentum balance or not. So according to angular momentum balance of diagonal elements should be 0. So sorry, should be equal. So sigma 1,3 is equal to sigma 3,1, correct? Sigma 3,2, sigma 2,3 is equal to sigma 3,2, correct? And sigma 1,2 is equal to sigma 2,1. So our angular momentum balance is getting satisfied. Now we need to check if it is satisfying our linear momentum balance or not. So how do we do that? Objective. Question number 10. So from matrix representation, you can see sigma 1 is what? X2 square plus some theta or maybe something. Let us write it as beta into x1 square minus x2 square. Okay. Sigma 21 is minus 2 beta x1 x2. Sigma 22 is, see how I'm able to get the information from this. You have to I'm from this matrix, I'm able to write that what is the component. You should be able to do that also. With practice, you will be able to do it. This is x1 square plus beta x2 square minus x1 square. And the sigma 33 part is beta into x1 square plus x2 square. So we have already checked AMB by telling that all octagonal elements are same. So AMB has been verified. Has been verified. Check LMB. So in LMB, what do we need? We need del sigma 11 by del x1. So what will be this? This will be 2 beta x1. Del sigma 12 by del x2. So it will be minus 2 beta x. Del sigma 13 by del x3. It is 0 because sigma 13 is 0. Okay, so I have a habit of writing tau12 as sigma 12 also. So you can write it as tau12 or tau13 instead of sigma 13. So and one more thing is given in the absence of body force. This means that our components B1, B2, B3, those are 0. So B1, B2, B3. These are 0. Let's see, some other condition is also given. It is telling that if it is satisfied. I'm so sorry, network is dropping today a lot, but I'm in my institute. I don't know why is it happening. So A is 0. So the first equation of LMB is what? Del sigma 11 del x1 plus del sigma 12 del x2 plus del sigma 13 del x3 plus B1 equal to rho A1. This is 0. This is 0. This is also 0. And here you can see this is 2 beta x1 minus plus minus 2 beta x1. So we are getting 0. So the first equation is satisfied. Similarly, we will find del sigma 22 by del x2. This is what 2 beta x2. You can see from here. If I differentiate this with respect to x2, this will be 2 beta x2. And del sigma 2, 3 by del x3 is 0. So the second equation is what? Del sigma 2, 1 by del x1 plus del sigma 2, 2 by del x2 plus del sigma 2, 3 by del x3 equal to b2 equal to rho a2. Now you can see one thing. The first index it is 2, 2, 2, 2. So this means that we are working in the direction of E2 direction, like in the second direction. So to remember, even for a general case, now, for example, here I will write 1, 2 later because this is a symmetric thing. But even for general case, this sigma 2, 1 means force on plane 1 in second direction, in direction 2, E2. Force on plane with normal in E1 and the direction of that force is 2. Similarly, here the force is on plane with direction with normal E2 and the direction of that force is 2. Same, and here the plane is having a normal E3 and the direction of force is 2. So you see, like this thing is like to just to remember that if you are writing the linear momentum balance in this second direction, the first index will be 2, and just you have to write, for example, for first E1, the differentiation is with respect to x1. For plane with E2, the differentiation is with respect to x2. For plane with normal in E3, the differentiation is in x3. So if we put everything, del sigma 2, 1 by del x1 is same as del sigma 1, 2 by del x1. So this is minus 2 beta. Sorry. Sorry, here it was del sigma 1 to del x2. So here del sigma 2, 1 by del x1 will be what? Minus 2 beta x1. Minus 2 beta x2. Sorry. I'm so sorry for repeating wrong thing again. Plus 2 beta x2 equal to 0. And you can see that this is cancelling. So we are getting 0. So the second equation, second LMB is also satisfied. Though it is an objective question, I'm just showing you the steps you have to follow. For subjective questions also, you will follow the similar steps. So this is just a warm-up kind of thing. Now for third direction, we know del sigma 3, 3 by del x3. What is it? I think it should be 0 because it is not dependent on x3. Del sigma 3, 2 by del x3, del x2 is 0. Del sigma 3, 1 by del x1 is 0. So if you put in third equation of LMB, it will be 0 plus 0 plus 0, 0 because of body force. So the third equation of LMB is also satisfied. Also satisfied. So we have seen that the angular momentum balance was satisfied just by saying the components of the matrix. We did not have to like derive everything. And to check LMB, we had to see like if our LMB1, like all the three equations of LMB are getting satisfied or not. So I hope this is clear to all of you that how will you approach a problem when you get a subjective problem. You will get this was also a subjective problem. It is listed in objective part of that PDF, but I think this was a subjective problem and we had to go through this exercise just to see if our like the matrix form which we have been given, if it is satisfying our LMB or not. So I will give you some other questions also. You can try other questions and you may ask me in the like next. If you come in the next lecture also, you can ask me there. So that for this question, you can count the number of unknowns after replacing the like sigma 1 2 by sigma 2 1, sigma 3 2 by sigma 2 3, and sigma 1 3 by sigma 3 1 in the stress matrix, and you will be able to solve this. So in question number 8, suppose we want to write the stress matrix at point E1, E2, E3 coordinate system, and we know traction components on E2 plane. How many stress components of the stress matrix are still unknown? So here they have given T2 plane. Suppose, so what they are telling is, so first thing, when you read this question, you should, like at the first step, you should go that, okay, I've read this in first week, and each column of this stress tensor, stress matrix. I should say it as matrix representation of a stress tensor. This is the correct one. Representation of stress tensor. I know this is in E1, E2, E3 coordinate system, so I'm writing it here. So what they're telling is this T2 is known. So if T2 is known, how many, question number 8, I think this is. Yeah. So how many stress components of a stress matrix are still unknown? So we know T2. What does this mean? Mean we know sigma 1 2, sigma 2 2, and sigma 3 2. Now if you if you invoke AMB, from there what do you know? Sigma 1 2 equal to sigma 2 1. Sigma 3 2 equal to sigma 2 3. Right? So what will happen? You already know sigma 1 2, so you know sigma 2 1 also. You already know sigma 3 2, so you know sigma 2 3 also. So the unknowns are, this is unknown, this is unknown, this is unknown, this is unknown, but these two are same. So it's better I write the sigma 1 1, sigma 1 3, sigma 1 3, sigma 3 3. So this is unknown, this is unknown, and this is unknown. So answer will be 3. The questions are really straightforward. You don't need to use very high-fi concepts. If you look at it with, if you have gone through the lectures properly, and if you have gone through any of the tutorials, either taken by me or Roshan, I think you will be able to solve these problems. They are not very tough. Now, this is the questions that I discussed in the class. Off-diagonal components of a stress matrix at every point inside a fluid body in rest. This is a very important key term. Fluid body in rest are 0. These will be 0 in all coordinate systems because the fluid cannot sustain shear. So in any coordinate system, shear will not be present. It does not matter. It does not matter what kind of coordinate system you are taking. If you are taking this, if you are, suppose if this is a fluid, it doesn't matter you take this surface. It doesn't matter you take this surface. Even if you are taking this, this if you're taking coordinate system according to like this surface, for example, this is your x1, this is your x2, and suppose coming out is x3, then also off diagonal term will be 0. Off diagonal term will be 0. So please go through these PDFs also apart from your assignments, and I think you will be able to solve these problems. Now I will take some other questions. So how about we take this question? I will take a variation of this question so that you can try this one on your own. Written questions here, so I will just use it for you. So let's solve a problem which will use our concept from first week also. So the question is, I hope you people are noting it, because the question is, we are given a stress distribution in certain body, and the matrix representation is given by sigma equal to 0, 100 x1 minus 100 x2. If some, I think two of you also attended my last session, so you may remember that there was one stress matrix given and I corrected it that it should be minus 50. So actually I did that because I knew that according to angular momentum balance, the off diagonal elements should be same. So you should be able to understand that if a stress matrix which is given, if it is correct or not. So suppose if I write minus 100 x1 here, then it is not a valid stress matrix because the AMB is not getting followed. It may be valid, but AMB is not getting followed. So it is not valid stress matrix for this case, for your case. In higher education, we also read about Piola-Kirchhoff stress or some other stress tensors where the off-diagonal elements were not zero. But for you people, the stress matrix is always symmetric. Just remember it. It should be what? Minus 100 x2. I'm not even looking at the question because I know if here it is minus 100 x2, it should be minus 100 x2. So we are given a stress matrix representation of a stress. Okay. We are telling we are being told that find the traction vector. Find the traction vector acting on a plane. Acting on a plane which passes through the point. So we are given a plane which passes through a point 1 by 2 root 3 by 2 comma 3. So this is a point we are given on the plane. But till now you can understand that we don't have any information about the normal. So now is the part where we will come to know that how do we get the normal. And it is written, and this plane and this plane is tangent to the circular cylinder surface. Circular cylinder surface x1 square plus x2 square equal to 1 at that point. So see, we are not in this particular question. The beauty of this question is they have not specifically mentioned you that what is the normal of this plane. You will need to use your mathematical concept to find the normal. So they are telling there is a cylindrical surface and I suppose this is a point on the cylinder. It is assumed. So first verify that if this point lies on the cylinder or not. So 1 by 2, so it will be 1 by 4 plus root 3 by 2. So that will be 3 by 4. So 1 by 4 plus 3 by 4, it comes to 1. So the point lies on this. So this plane, which they have given, this is a tangent at that point. So here it is a tangent. So how do you find the normal of this plane? So what we can do, we can find the normal of the surface, cylindrical surface at that point, and that will be the normal of this plane, whatever plane we have. So how do you find the normal? I will write it with other color. Maybe I'll write it with blue, sorry, black color. So normal on the cylindrical surface, on the cylindrical surface is what? If you have gone through mathematics, you will know that suppose if f is the equation, this equation, the first I will have to write. Wait, just give me. Yeah. So f is what? X1 square plus x2 square minus 1. So normal, suppose this, if I'm calling this as n, so n will be gradient of f divided by norm of gradient of x. Now you know that gradient of f, this will give you a vector. The generic formula for gradient is what? So for suppose if f g is a scalar, so you can write it as so here what will happen if I differentiate f with respect to x1? We will get 2x1 e1 plus 2x2 e2. And in terms of e3, it is zeros, like there is no e3 term here, so it is 0 divided by square root of. So what will be the modulus? Sorry, it should be better now. So 2x1 square plus 2x2 square. So normal is so this is for any point. This equation is for any point. Now we are given a specific point where we have to find the normal. Now for this particular case, one thing you can see is x1 square plus x2 square will be 1. So I can directly replace it here, but I will show you for a generic condition. So n at point 1 by 2, comma root 3 by 2, comma 3. And at point this will be 1 by 2 e1 plus root 3 by 2 e2 divided by 1 by 4 plus 3 by 4 square root. This is what? E1 plus root 3 e2. So this is what we will get. This is the normal. And you can also check that like here also, if you remember in last class, I told you that whenever you find normal, you check that the Modulus of this normal is unit, like it is 1. So in this case, it is 1 because we have already divided it by its magnitude. So in this particular case, this magnitude was 1, so it didn't make a difference. But suppose if del gradient of f had a magnitude 2 or 4, there you would have got wrong result if you had not divided by this magnitude. So remember this formula. So now we already have our normal with us, and we have our stress matrix at that point. So what we can do to find traction, we can directly write T equal to sigma into that point X into N. Now why is this N and this N same? Because this N which I have found here, this is the normal on the cylindrical surface N. Normal on the cylindrical surface, like this cylindrical surface. But this plane is tangent at that point. Means the normal of the cylindrical surface is also the normal of this plane. So that's why I was able to write that. So what is sigma at that point? This will be minus 100 x2. So it is minus 50. Sorry, it was 100 x1. So it is 50. So here it is 52. Minus 100 x2. So it will be minus 50 root 3. And where it should be minus 50 root 3. Normal in column form will be what? 1 by 2 root 3 by 2 and your simple matrix product is here. Matrix multiplication is here. So what we are getting is T root 3 by 2 So this is our final answer. Suppose if we go one more step and they tell you to find the like traction acting in the normal direction. So what you will do, you will simply do T dot N, value of traction in the normal direction. So what will this be? 25 root 3 E1 plus E2 minus root 3 E3 dot 1 by 2 E1 plus root 3 by 2. This will be what? So this is our answer. This is our answer. But this is what I'm trying to find. Find the magnitude of normal of traction, normal traction of normal traction. So whatever they have asked in the question, this is the final answer. This is something extra I'm doing. I'm reiterating this so that you do not get confused that why did I. This is the answer. Tn is what? E dot n equal to 25 root 3 by 2, because E1 dot E1 will be 1 and E1 dot E2 will be 0. Similarly, E2 dot E1 will be 0, E2 dot E2 will be 1. So it is root 3 by 2, and E3 dotted with these two will be 0. So this is 25 root 3. Do you have any doubt till now? So I will give you a question. Try to solve it. How will you do it? So suppose we are given a stress matrix in the E1, E2, E3 coordinate. And this is nothing fancy. This is very easy. Suppose if we are given sigma 11, sigma 12, sigma 13, sigma 12, sigma 13, sigma 23, sigma 3. Here it is sigma 3. Okay. So we are given this. Now we are telling our new coordinate system is formed. New coordinate. Generally, you have seen the rotation matrix form. R equal to C theta minus S theta, S theta, 0, 0. This form is when rotation was about E3 axis. So you had a E1, E2, E3. So you rotated about this. So you got new E1 hat, E2 hat. What I want you to do, I want you to think that I'm rotating about E2 axis. So in this, that case, what will be the rotation? Rotated about E2 axis. Rotated about find a rotation matrix to rotate E1, E2, E3 coordinate system about E2. So the form of R will be slightly different. It will not be the usual form. This will be cos theta, this will be 0, this will be 1, this will be 0. Hello? Hello? I think my net went away. I think I'm reconnected now. So I hope you people are able to hear me. So here it will be 0, it will be 0. This will be sine theta, and this will be cos theta. So this will be the rotation matrix representation. If we are rotating our axis about E2. So here what is happening? Suppose this was our E3, E1, E2. If we rotated about E2 here. So this is E1 hat, this is E3 hat. So this is how rotation will be formed. So if in examination, the question comes where it is written that your rotation has been done about E2 axis. Suppose if it is rotated about E3 axis, even axis, you have to choose the rotation matrix according to that. People become very used to of using the rotation tensor, rotation matrix written when we are rotating our coordinate system with respect to E3 axis. And that should not be the case with you. So another homework for you people is find rotation matrix. Find rotation matrix. Find rotation matrix when E1, E2, E3 needs to be rotated. Needs to be rotated by which from E1 axis. Okay, so I will just give you one hint. You see, when we rotated about E2 axis, the rows and columns of E2 axis, except the term A22 is 0. Like off diagonal term is 0 for second row and column. So the same thing is true for this matter. You can see here this A33 was non-zero and other terms were 0. So the same thing will happen when you rotate about even axis. So just keep this in mind. You can use the definitions I gave in first lecture and you will be able to do it. I hope I was able to cover most of the things which will be I was able to cover all the things in the which was taught in week 1, week 2. And I've shown you how to use those concepts to solve problems. One thing to keep in mind is no problem will be specific to a particular concept only. You will have to use the concepts taught in different weeks or in different lectures. So for that, you need to practice. So practice from the PDF from the link which I have shown. I will again show you the link. I will, like in my YouTube channel, I will add this link also, and I will upload this PPT also. So from there also you can get this link. This is our professor's link who is taking this course, and there he has given you the notes. Now, one thing which I will show you is okay, just give me one. So to access the PDFs, you will have to actually do the right click here and click in open in new tab. Then it will open. If you directly click on it, if you do a left click on it, okay, it is opening now. Earlier we had to do the right click and then open. So it's a good thing. So you can get the PDFs from here and you can practice the questions which are at the end. And I hope this session was helpful for you. Thank you all. This will be all from my side. We will meet again in next week on Tuesday. Again, my name is Manoj Shikhar. I'm a PMRF scholar at IIT Delhi. And these sessions I will take on Tuesday from 6 to 8. Thank you for joining me. Thanks all. If anybody has any question, you can ask here, or we will just end this meeting otherwise. Any one of you has any question? Okay, so I will. So I understand that nobody has any questions, so I will be ending this meeting. Thank you everybody for joining. Have a great day.